Our next speaker is Dennis Ramdass. He's Director of Engineering at VMware. He used to be at Bracket Computing, and I was like, oh, well, that's interesting, but they were bought out by VMware. And he's the only speaker whose talk was delayed because we couldn't find the bell. So again, if you know where the bell is, please tell me. And his word of the day and term to describe himself is lifelong learner. Welcome, Dennis.
Hi, thank you, Beverly. So I'm Dennis Ramdass, and I'm here to talk to you today about building a security analytics platform using federated machine learning. So the code name we have for that is Project Trinidad. So fun fact, I'm from Trinidad and Tobago, like the director of this conference, Mark. So that's a fun fact for you. I am with VMware in the Office of the CTO in the Research and Innovation org. So I'm not a lawyer, but I have to put this slide in because we are showing you tech preview code. I'm not going to go through this, but when the slides are distributed, please note the disclaimer. So on the agenda today, I'm going to tell you a little bit about who I am, who we are at VMware, a little bit about Project Trinidad. There'll be a demo. The demo is around 5 minutes long. It's a video demo, so kick back, relax, enjoy that. And then we'll get a little bit deeper into the ML components of the talk, so ML, federated ML, and what's next. So let's jump into it. So who we are. So how many people here know VMware and know what they do? With a show of hands. Okay, good, like about half the crowd. So VMware is an enterprise infrastructure company. We started off with server virtualization. Now we do a lot more, networking, security, modern apps. So that's what VMware does right now. We sell primarily to enterprise customers. So I am part of the Office of the CTO in the Research and Innovation group. So I am part of this unit called X Labs. So what X Labs is, it is one of the buckets of funding that we have in research and innovation. So I'll just quickly tell you about the 3 buckets. First of all, we have research, which focuses mainly on problems in academia, delivering state-of-the-art content and papers in that field. Then we have the incubation group that takes the best ideas from research and industry and do technical validation of that. Now the 3rd bucket is X Lab. So this is advanced development. So we're looking to take ideas from incubation, from research, and put them into production products. So we want to deliver things that are 1 to 3 years ahead of usual VMware product roadmap and try to be industry leading in that regard. So some of the focus areas that we have here are listed on. I'm not going to go through all of them, but we run it kind of like a VC would run its portfolio. We have little startup projects in all of these areas. So of particular interest to me is Edge and ML. So if you are running ML inference on the edge or that's a problem you need to solve, you can find me and we can talk about it. This talk is not going to be about that particular piece. We're going to be highlighting the modern apps and security part of things and using ML to power a project that we have. So, Project Trinidad, what is it? Yes, big up Trinidad. So, this is the slide that tells you security is important. I don't need to tell you that, but essentially we want to target modern architectures. So think architectures that have east-west microservice traffic. So essentially, think of it as we want to secure your Kubernetes cluster and detect intrusions and security threats. So what we built to solve this problem is an API security and analytics platform. So we decided to build something that collects the API traffic between your microservices. So we used an eBPF sensor to do that. But the main piece I'm going to highlight today is the SaaS analytics platform that's powered by ML. So in our first iteration, we're doing real-time anomaly detection of API calls and sequences. So this differentiates itself from other security products because we use ML heavily, and we look at not just HTTP metadata or typical network intrusion detection signature-based methods. We actually use ML to look at the payloads, look at the API parameters, and understand the business logic of the applications, model that with ML, and then use anomaly detection there. So here we have about a 5-minute demo. So sit back, relax. This is about our entire product. And I'll dive deeper into the ML piece of things here. So hopefully this video works.
In this video, we are showing Project Trinidad, VMware's API security and analytics platform. Project Trinidad is a solution to secure microservices in Kubernetes workloads by performing machine learning on API request and response data. The data is captured in a customer's Kubernetes cluster using a sensor built on eBPF technology. The sensor captures API traffic entering and leaving the Kubernetes cluster, typically referred to as north-south traffic, as well as east-west API traffic between microservices within the cluster. Captured API traffic is enriched with Kubernetes metadata, aggregated and converted into the OpenTelemetry data format before it is sent to the VMware SaaS backend. Project Trinidad is designed to be cloud agnostic and work with many common observability tools that support the OpenTelemetry data format. Our machine learning services live in a centralized, multi-tenant cloud backend. Their purpose is to analyze captured API traffic and learn patterns of expected benign activity in the customer cluster. Even while machine learning classifier training is ongoing, users can use the Project Trinidad UI and query service to gain insights on their workload API data and draw valuable conclusions from the collected data. Once the machine learning component has captured enough API data to train a well-performing model, the analysis services start annotating newly arriving API data and matching activity against the learned benign baseline. Any outliers are flagged as anomalies, and the user is notified of unexpected and potentially malicious activity in their Kubernetes cluster. Today's demo will show the deployment of the Project Trinidad sensor in an existing Kubernetes workload cluster. Next, we will show how the query service visualizes incoming data in real time and how the machine learning classifiers are trained. We will then simulate an attack on the workload application using the log4j exploit, and we will see how Project Trinidad highlights the anomalous behavior in the UI. In the demo Kubernetes environment, I've already installed a sample e-commerce application that allows a user to buy various types of socks. The workload application is running inside the Kubernetes namespace called SockShop, and it consists of several services and API endpoints. We'll be using the service called Frontend to access the SockShop UI. Before we begin interacting with the application, let us install the Project Trinidad sensor to capture and analyze API data. I've already requested a demo account and received a personalized link for my account into the onboarding page in the VMware Cloud backend. Here, we see the instructions on how to deploy the Project Trinidad sensor into the workload cluster. In the download package section, I can either download the Kubernetes manifest for deploying the sensor, for example when using GitOps workflows, or use the shell instructions provided directly on the page. For this demo, I will do the latter and copy and run the instructions directly against my Kubernetes cluster. The command will first create a new Kubernetes namespace called Trinidad, download the needed sensor manifest from the onboarding API, and deploy the resources into the newly created namespace. The Project Trinidad sensor deploys as daemon sets on each Kubernetes node for collecting API traffic, as well as a dynamically scaled collector component for aggregating and uploading data to the VMware SaaS backend for analysis. Once all sensor pods have been launched, we can start interacting with the SockShop demo application. I register as a new user and add my favorite socks to the shopping cart. These actions are observed by the Project Trinidad sensor. We can view and analyze the API data in real time in the UI. The sensor captures detailed information on each API request observed in the workload cluster, including URL, request and response headers, and other connection metadata. The request we are seeing was annotated by our machine learning pipeline, indicating that no model had been trained on the workload API data yet, and that the request is included in an automatically triggered model training. Model training happens on individual API calls and their parameters, including payload and headers, as well as on sequences of API calls, regardless if they're between users and external API endpoints, or internal API calls between microservices within the application. Training continues until the machine learning components have gathered enough data to make reliable predictions on newly observed API data. The collection and training time depends on the volume of data observed, but typically completes within hours of installing the sensor. Let us now skip forward until the system has captured sufficient data to complete training so that we can perform inference and tag newly arriving API data as benign or anomalous. For this, let's log into the sample application once more and observe the requests in the UI. API logs are now annotated with tags indicating if an anomaly has been detected. In this case, the observed activity is part of the expected benign application traffic and tagged accordingly. Let us now simulate an attack against the Sockshop application using the recent log4j vulnerability. This attack script triggers requests against the login API while injecting a header containing the log4j exploit. As this behavior constitutes abnormal behavior that we have not observed during the model training, the machine learning inference should flag these requests accordingly. Let us now observe the same attack through the UI. Our machine learning pipeline is comprised of many features that are assembled together to perform a binary decision on each API request captured by the sensor. Amongst these features, the system analyzes request headers, including the ones manipulated in our simulated attack. As we can see, the attack API request that the sensor captured is flagged as an anomaly, and we can also see the extra headers injected by the attack script. In today's video, we saw an end-to-end demo of
All right, I'll stop the video there and let's get a little bit deeper on the ML components here. So that should give you an idea of the problem we're trying to solve. In this demo, we showcased the log4j exploit, but we really want to protect customers' infrastructure from future exploits, zero-day exploits. So that's where ML comes in. We don't want to have to look for the log4j signature, right? We want to be able to detect if something is different. So this is what our training pipeline looks like for machine learning. So we have two pipelines. One is for individual call analysis, and one is for sequences. So we build a model or a set of models per customer, essentially. So what we do is we do some data pre-processing. We don't have control over the customer data that comes back to us. We may need to deal with duplicates, dropping null values, et cetera. So in both cases, we do that. And then we have a model building phase. So in the model building phase, we do some feature engineering to input into our model building. So most of the data that we deal with is tabular. We deal with the payloads of these API calls as well. So it could be unstructured, it could be JSON, but mostly it's tabular data. So then we build different types of models for the individual API calls. So we use gradient forests, we use gradient trees, we use isolation forests, we use a number of different ML model techniques. And in a traditional ML techniques, in addition to some deep ML techniques like CNN, autoencoders. Then we do ensembling at the end, where we do averaging and we do some voting to make a binary decision of whether an anomaly was detected or not. Now, for our sequences, we follow a similar set of steps, but we use LSTM for our modeling of sequences to detect if something in the sequence is out of order. That's usually the case that we're trying to detect. So jumping forward, some of the challenges that we're facing and some of the approaches that we've taken. So the primary challenge for us is that the target customer is not an ML expert, and they're really not an application expert either in the application that's being monitored. So our approach is we use a combination of heuristics together with ML. We try to make really explainable anomalies. So we try to build that into our models themselves. So selecting features that are highly explainable. We also use SHAP to highlight features that have contributed to the decisions that have been made. And we really want to focus on unsupervised or weakly supervised machine learning because we cannot depend on the customer to label data for us. So another big problem that we're facing and we're dealing with is data drift, right? So data drift, in this case, if a customer upgrades their infrastructure or application, the form of the data may change, right? So we need to retrain our models when that happens. So we have heuristics that check for when your application has been upgraded, and we do model retraining. We're also experimenting with different forms of online training to help deal with new data as it comes in. Then we also have the gradual data drift problem. So this is the problem where the customer application, the users of that application, their behavior may change over time. So think of the Sockshop example. On Black Friday, a lot more users may be using Sockshop than before. We don't want to flag that behavior as an anomaly per se because it's not a security threat. So again, we have heuristics. We have a data drift detection module that tries to specifically call out data drift so that we can retrain our models on that. Being a security product or analytics platform itself needs to be secure. We have to improve the overall security posture for the customer. So what that means is we are the target of ML-based attacks, right? So we have to implement some counter-adversarial ML techniques, and we're using GANs a lot for this right now. This is still in an experimental phase, but using GANs to generate adversarial data, having our ML be able to detect if the model is being poisoned during training, or if a user is trying to bypass the anomaly detection in there. One key thing here that we're building is we are doing, this is a real-time online system. Anomalies are very rare, but it's critical that we capture it because it could be a security threat, right? Like that's what our customers are paying for this product for. So that means our pipeline has to be scalable, performant. We have to be able to ingest a massive amount of data, run inference on all of it relatively quickly. So our target, SLA for that is 60 seconds for inference for an individual API call, and for sequences, we have, within a couple minutes. So we're also trying to figure out the cold start problem, right? So a customer just installs our sensor and hooked it up to our platform. They don't want to have to wait days to get a trained model to then say they're secure. We want to, kind of secure them from as soon as possible. So for the cold start problem, we are looking at, different forms of transfer learning to transfer learnings across customers so that, the new customer can benefit from all the info that we've had and the model building. And we're also experimenting with federated machine learning. So I'll talk a little bit about federated machine learning in the next couple slides. And then another key point here is we are looking at a bunch of sensitive customer data, PII data, secrets. So we need to handle them carefully, but more than that, we've implemented, differential privacy techniques where we can mask some of the raw data coming from the customer, de-anonymize certain pieces of data, and we're also experimented with federated machine learning as a way to keep the data local to the customer so that they don't have to share their private data. So that's my segue into federated machine learning. So how many people know about federated machine learning or have implemented some federated machine learning? Not that many. Okay, good. So this federated machine learning is very simple. I'll build out this slide because it's a cute sheep animation. But essentially, on the left-hand side, we see traditional machine learning where the data moves to a central location for the model to be built. So you see all the food coming to the sheep in the middle. On the right-hand side, that's the paradigm of federated machine learning where the models go to where the data is and we run inference at the customer site. So there are a few ML techniques that enable this to happen, and that umbrella is called federated machine learning. Obviously, it has huge benefits for privacy, but the biggest benefit for us is it's a large amount of data that customers are generating. It's a huge network cost for them to send that across the network to us. So that if we can do inference locally, it helps a lot. So like I mentioned, there's also, we want to share insights across customers, but customers don't want to share raw data with each other, right? So we want a system where they can all benefit but not share raw data. So with federated machine learning, the weights are the only thing that gets transferred up and down to a centralized coordinated server. So there are periodic updates that happen, and this works well also for customers that may be network disconnected for a while, and we do have security conscious customers like that. So they can tailor their updates for the model weights. So in our case, we are looking at horizontal machine learning. So if you're familiar with federated machine learning, there are two basic flavors, vertical and horizontal. Horizontal is where different customers share the same feature space. So customer A and customer B may be running similar applications in their cluster. Say they're running Jenkins or something like that. We want customer B to get the benefit of having the model learned about Jenkins from customer A. So that's horizontal machine learning. As I mentioned, these are the benefits that we talked about, the network cost, the overall cost, solving the cold start problems, and keeping sensitive data locally. So what we've experimented with so far, and we have a blog out about this that just got released last week, is we're experimenting with OpenFL. So OpenFL is an open source framework coming out of Intel. KubeFate is another popular one that's more for the vertical federated machine learning use case. For the horizontal one, OpenFL is a little better suited. So what we did is we ran some experiments for our anomaly detection. We used 2 sample applications, so Online Boutique and Hot Rod. So if you're familiar with microservices, these are just the canonical demo ones. And we tried to figure out, hey, are we getting good results over different rounds of training, and are they converging? So one problem with federated machine learning is sometimes you get worse results and non-convergent results. So we found pretty good results for both types of applications. So these applications behave a little bit differently. So far we've seen pretty promising results with federated machine learning, and that's something we want to push to production. So jumping to the next slide, we want to enable this for customers in production. Right now it's in experimentation phase. There's a bunch of work we need to do on post-processing anomalies. So right now our system just has anomaly detected and has a basic reason that says, hey, maybe it's this feature, and this feature could be this parameter inside your HTTP call. That's not really good enough for a security operator to make a decision what to do. So there's a bunch of post-processing we need to do. In addition to anomaly explainability, there are things we need to do to hook it up to existing rule-based and heuristic systems to say, okay, this may be this certain type of attack, right? This could be a malicious insider. This could be remote code execution. So those types of insights we hope to get from our ML, but we also are implementing a heuristic system on the back end to help explain our anomalies. False positive reduction. So this is super important. So if you have ever worked on anything in the security or cybersecurity field, if you have a product with too many false positives, no one's going to take it seriously and buy it, right? So that is one of the inhibitors that has stopped companies from developing ML-based security solutions. The false positive rate has been too high. Now, we think in our specific use case with microservice to microservice API traffic, we've seen data be very regular, and there's a reason for that. The reason is most microservices communicate using a schema, using something well-defined. So our models essentially capture the schema implicitly and also capture sequences of calls implicitly. We're also looking at customers who want to participate in weak supervised learning or reinforcement learning, enabling them to do that in a way that's easy for them to use. So some of the talks have talked about weak labeling and things like that. And then the last point that I want to mention is all the ML that we do for this product right now is under the hood. So it's not available to the customers. But we do have large enterprise customers who have their own data science and ML teams, and they may want access to the models and the underlying pipeline to be able to make tweaks or changes or improvements to it. So that's where we're heading next. So we have a few minutes for Q&A, so I'll pause here.
So do you pass? Oh, thank you. My question is, do you actually pass the model training, everything to happen on your client side? Is that what you mean by the federated machine learning? Also, that's first question. And then the second one is there a specific type of data for which you prescribe this method versus any type of method, any type of data you think will benefit from such an approach?
Yeah, sure. Great questions. For federated machine learning, yes, the training and inference happens on the customer site. So the demo we presented, we have a SaaS cloud backend. Customers can also run this solution totally on-prem, and then federation is a additional step on top of that. So they can opt into a federated solution where they say, okay, I trained my model, I want to communicate the weights up to a centralized server that can distribute those model weights to other customers. So yeah, all the training and inference happens on the customer side. The second point about different types of data, so we've been focused primarily on on API call data, and the format that we chose to ingest for our ML pipelines is OpenTelemetry data. So OpenTelemetry is an emerging standard for observability in particular, so logs, metrics, traces. So we think that ML on OpenTelemetry traces is going to be big. So that is the area that we're focusing on, OpenTelemetry traces. So.
All right. Awesome. Thank you so much.
All right. Thank you.